Today I am going to teach you Gauss law and its application. And first of all, we will discuss about Gauss law. So, suppose this is my closed object and it contains a charge q. So, if I want to explain Gauss law, then I will just write the formula phi equals to q by epsilon naught. What does it mean? It means that electric flux passing through a closed object is equal to 1 upon epsilon naught times the charge enclosed by the surface. Electric flux passing through a closed object is equal to 1 upon epsilon naught times the charge enclosed by the surface. So if I want to write the definition, then it can be written like the electric flux passing through a closed object is 1 upon epsilon naught times the charge enclosed by the object. Okay, now if, as you can see, phi equals to q upon epsilon naught. Now again, the formula of electric flux can be written like closed integral of E dot ds, where E is electric field and ds is surface area. So if we combine these two equations, we get E dot ds equals to q upon epsilon. And this formula is going to be very useful. This formula is going to be very useful because with the help of this formula we can find the electric field intensity due to various objects. Okay, now as you can see here, we will find the electric field intensity due to uniformly charge. Suppose this is my wire and charge, its length is L and charge is uniformly distributed over its length and its linear charge density is lambda. Its linear charge density is lambda. So before solving this application, we will draw a Gaussian surface around it. Okay, so this is my Gaussian surface, and there are now three surfaces where electric field lines can be passed through. First, this curved surface. Second, this one, and third is this one. So as you can see, okay, so we will just find the electric field intensity due to only this curved part, because due to these two parts, electric field lines and surface area are perpendicular to each other. So angle will be 90 degree, and as you can see the formula E dot ds equals to so E dot ds can be written like, I am just writing this E dot ds, E ds cos theta. And if the angle between electric field and surface is 90 degree, so electric field will be 0. It will be 0. Okay. Okay. As we know that its linear charge density is lambda. So here you can see with the help of Gauss law, E dot ds equals to q upon epsilon. Okay, first of all, I will just write the value of lambda. Lambda equals to q by L. This is linear charge density, and here we can find the value of q. Q equals to lambda. So I will put the value of q in this equation, and again, as I had told you already, that we will find the electric field intensity only through the curved part. Okay, so ds, the area of this curved part is 2 pi r, as we know that the CSA of a cylinder is 2 pi r. This r is the radius of the Gaussian surface, and in case of q, I will write lambda L epsilon naught as it is. Now I have to find the value of this E. So lambda L over 2 pi epsilon naught R L. So it can be written like lambda over 2 pi epsilon naught R. If I want to draw the diagram graph between E and R, on one axis I will take electric field intensity E, and on another axis R. As we can see that electric field and R are inversely proportional to each other. E inversely proportional to each other. So it can be the graph of E versus R will be like this. Now, the next application is electric field intensity due to uniformly charged spherical shell. Okay, so first of all, what is spherical shell? Actually, it has a vacancy inside a spherical body. So, if I give the charge on this spherical shell or hollow sphere, all the charge will reside on the outer surface of this shell. Okay, now there can be three regions where we can find the electric field intensity. First, inside the sphere. Inside the sphere. Inside the sphere. So to calculate electric field intensity inside this sphere, we will draw a Gaussian surface inside this. Okay, let capital R be the radius of this spherical shell and charge is uniformly distributed over its surface. And this is my Gaussian surface and its radius is smaller. As okay, first of all, we will use Gauss law, and Gauss law is closed integration of E dot ds equals to Q by epsilon. Okay, now as you can see that the whole charge resides on its outer surface. The charge inside this sphere is 0. Q inside equals to 0. So I can write in place of E as it is E ds. In place of this, we will write the area of this spherical Gaussian surface, and it can be written like 4 pi small r square equals to, in place of charge I will write 0, so it means the whole term becomes 0, and again E can be 0. So electric field inside a spherical shell will be 0. Second region where we can find the electric field outside the sphere or outside the shell. Outside the sphere. For outside the sphere, we have to draw this Gaussian surface outside this spherical shell. This is my spherical shell, and again let its radius is r, small r. Okay. To calculate electric field intensity, we will use Gauss law, and it can be written like closed integration of E dot ds equals to Q by epsilon naught. Now, as you can see, the whole charge resides on the outer surface of this sphere, and this sphere is inside this Gaussian surface. It means E as it is. Now ds. In case of ds, I will write the formula of Gaussian surface 4 by r square. And as I had told you that the whole charge resides inside this Gaussian surface, so it means the total charge, as we had already given, Q upon epsilon. Now E equals to Q. I am taking this 4 pi r square in denominator, so it can be written like 1 upon 4 pi epsilon naught Q by r square. This is my expression for outside the sphere. Okay, so the third region will be, third point where we can find the electric field intensity is at surface. At surface. From the diagram, as you can see, if we are talking about inside the sphere, it means the radius of Gaussian surface is less than the radius of the sphere. Outside the sphere, the radius of Gaussian surface is greater than the radius of spherical shell, and at surface means the radius of Gaussian surface will be equals to radius of spherical shell. So Gaussian surface for at surface will be drawn at this point on this line. Okay, so to calculate this electric field, we will just put capital R in place of small r in this formula. So we get E equals to 1 upon 4 pi epsilon naught Q by capital R square. Now, if I want to draw the graph between E and R, E on this side E and here small r. So how can we draw the graph? Suppose this is my point capital R. On the left side of this capital R, this is inside the sphere. This region is inside the sphere, and this region is outside the sphere. Okay. As you can see that inside the sphere, electric field intensity is 0. So this is the graph for this expression. As you can see that at surface, electric field is independent of small r, so it will be a constant value. And at outside the sphere, electric field is inversely proportional to r. Okay, so it means the graph will be like this. So the graph for a spherical shell, hollow sphere or conducting sphere will be like this.